Hello everybody. In this video I want to show you something very interesting. Given this function y is sine x, I want to find the nth derivative of y. So that's dn dxn sine x. And I want to find a function. You'll see what I mean in a minute. Usually, if you give this question to people, they will give you a bunch of different answers, like piecewise. But I want one function of n and x. Okay, we can begin. You'll see what I mean. The first derivative is cos x. Okay. Second derivative is the derivative of cos x. That's minus sine x. So far, very easy. Third derivative is minus cos x. And then the fourth derivative, we are back to the beginning. Minus minus is plus, so it's sine x. So we're back to the beginning. We have only a few unique possibilities, and then we repeat everything. Now, you know, people want to join this together to create a function, one function, for the nth derivative, and I've seen some really fantastic and desperate efforts to join everything together into one function. Now, people using integer part, they're using mod arithmetic, like mod 4 or something, and other. I mean, these are very valiant efforts, you know, powers of -1, and they somehow combine this with maybe some piecewise if then else, but that's not what the approach I'm going to take. I'll show you a beautiful way to do this, a beautiful way to get one function as an answer to this question. First, let's review some things that we will need. This is the function sine x. It has one period of 2 pi, and this is here 3 pi. Okay, and you notice that sine x begins at 0 and goes up to 1, and you have to remember this. It begins at 0. That's a critical thing. If we flip sine x around the x-axis, we get something like this way, this way, this way, something like that. And this actually is minus sine x. So keep that in mind too. This is very important to remember. So we have here plus sine x, positive sine x, and negative sine x in this one graph here. Now let's have a look at cos x. Cos x begins at 1 and ends at the period, okay, at one period, goes back to the beginning. It ends here, well, it doesn't end, but it goes back to the beginning at 2 pi. All right, so always keep this in mind. It begins at 1. We will need to know this, like to be able to identify these curves quickly. So you identify them by seeing where they begin. And if I flip this around, let's see, this is more difficult to draw, but if I flip this over the x-axis, I get freehand. Okay, that's not so bad. I get minus cos. Okay, great. So now you can see in this one picture, we have both positive cos and minus cos. We see what they look like. We can identify them immediately, and that's very important for what we're going to do next. So look at what I've done here. I have shifted the origin by pi over 2. And how did I do that? Well, if I take any function and I add to the argument x pi over 2, or I add some value to the argument x, I'm shifting the origin to the right. This is one way of looking at it. So if I take any function, f of x, and I add to it some angle or some value phi, I'm going to shift the origin to the right. It's the same thing as shifting the curve itself to the left, but actually I prefer to reason about moving the origin. You'll see it's easier to draw and it's easier to think about. So I move the origin here to pi over 2. Okay, so what does that do? Well, this was sine x. My original curve was sine x, the blue curve. But now that the origin is here at pi over 2, well, we're at 1. And what is that? Well, that's this. That's cos x. Cos x. So we have now cos x by doing this shift. Okay, and what? Oh, lo and behold, look at what we see. We have the first derivative here. Okay. Now let's shift the origin a little bit farther. Now we're shifting the origin to the right by 2 pi over 2. So we'll take multiples of 2 pi. This one's 2 pi over 2 or just pi. But let's write it explicitly, 2 pi over 2. So when I've done this shift, now I look at my curves up here. What do I see? Well, this is exactly the same thing as minus sine. Okay, I'm starting at 0, but I'm flipped the other way around over the x-axis. So I have now minus sine x, not cos anymore, but minus sine x. Minus sine x. And lo and behold, I look up here and minus sine x is my second derivative. Wow, very interesting. Let's keep going with this idea. Let's see where this idea leads us. All right, so now I have shifted the origin by 3 pi over 2 to the right. Okay, so I've done this shift, f of x plus 3 pi over 2. So that shifts it all the way over to here. And my origin here is, at the origin here, the curve now begins at minus 1. So this, if I look back at my original review curves here, this is minus cos. See here? Begins at minus 1. Great. So we have now minus cos of x. And what is that? That is the same thing as our third derivative. So third derivative is done. And I think I need one more. Let's see. Okay, so now I'm shifting. Let's go back to black. I'm shifting by 4 pi over 2, but that's the same thing as 2 pi, and 2 pi is 1 period, so I should come back to the beginning, and indeed I do. When I shift all the way out here to 4 pi over 2, I'm back to beginning at 0, and then the hump goes up, so I have sine, so my result here is sine x. And let's compare to the derivatives, and yeah, we have it here, this. So we've done all of them, and we've seen how it works now. There are no other possibilities. We see then that the nth derivative of this, dn by dxn, sine x, this is sine, and we look at these results, and it's clear that this is x plus n pi over 2. So I have one function of n and x, and there's no mod arithmetic, no minus ones, no if then else, no piecewise type definitions. We have one result, and this, I think, and I'm sure you agree with me, this is really beautiful, really beautiful. Problem 2. Y is cos squared x. We want to find the nth derivative of this. This is y, n, and we want it as a function of n and x. We don't want pieces. We don't want if then else. We don't want mod arithmetic. We don't want powers of -1 with integer parts. We want just one function. All right, so let's do some calculations first. So y1, first derivative is -2 sine x cos x. And this, by trig identity, is minus sine 2x. Okay, so that's the first one. Now, second one, second derivative. I take the derivative of minus sine 2x. The 2 comes out, minus 2 cos 2x. And I want to write it in a bit of a special way, like this. I want to take this minus sign inside and leave the 2 outside. You will see why. Cos 2x, like this. Now, y 3, third derivative. Well, it's going to be another power of 2 that will come out, 2 power, and derivative of cos is minus sine. So the 2 minuses cancel out, and I have sine 2x. Very good. And finally, one more. 2 power, well, actually 2 more. We'll do 2 more. We'll do it until we come back full circle. You get the pun? Full circle. It's a math joke because we have circular functions. Okay, so one more derivative. We have 2 cubed cos 2x. That looks good. And let's do one more. Y. Fifth derivative. This is, okay, derivative of cos is minus. So minus 2 power 4 sine 2x, yes, and I'll write this in a special way, 2 power 4 minus sine 2x, like this. Okay, first thing to notice is that we have this factor of 2, which is powers of 2, which appears here. We have 2 power 0 here, 2 power 1, 2 power 2, 2 power 3, 2 power 4. So we have this factor of 2 power n minus 1 in front of all of these functions. All right, and to duplicate the same kind of analysis that we did the last time, let us do some review. We'll look at the fundamental curves. Sine 2x, this runs faster, oscillates faster than normal sine. This up here, this is 2 pi, and this here is pi. So you see, in just pi, it does one full period. Okay, so it's 2 times faster than regular sine. And if I reflect this over the x-axis, just like last time, you see what I get, and you must keep this in mind, that this gives me minus sine 2x over here. Okay, and both start at 0. All right, and end at 0. Okay, this is very important. That way you recognize them. When you see them, you recognize them. So this is minus sine 2x over here. Likewise, cos 2x, another fundamental one we need. It begins at 1. And it's easy to visualize its negative. We just reflect it over the x-axis like usual, and we get minus cos 2x. So now we understand sine 2x, cos 2x, and their negatives, and we see how they work, and we can easily identify them when we see them. Here I'm starting with cos 2x, and I will shift it to the right by just a little bit, by pi over 4. Let's see what happens. Now watch what I'm doing carefully here. I add pi over 4 to x. That causes the shift in origin here. I do not do this. Do not make this mistake, okay? Don't do something like this. You see what I've done here? It's not the same thing. Here I'm shifting 2x. It's not the same thing as shifting the x, the origin. Okay, so this is wrong. This is a mistake I see often. It's a mistake I have done many, many times. You add it to the x. if you want to shift the origin correctly. And what does this give us? Well, you can recognize this immediately. This is minus sine 2x. Minus sine 2x. And do we have this in our functions that are derivatives? Yes, we do. Now you see why I wanted to write it in the special form. It's easier to identify. So we have the first one. It's a shifted form of cos 2x. Shift again by a little bit. We'll shift now by 2 pi over 4. So this is f of 2x plus 2 pi over 4, or pi over 2. But let's be explicit. And again, don't make this mistake. Don't write 2x plus 2 pi over 4. You're not shifting the origin when you're doing this. Okay, this is wrong. This gives us, we can immediately identify this. You see it's starting at minus 1. Okay, so that's minus cos 2x. Minus cos 2x. So let's go back. Do I have it? Yes, here. This one has been identified. We have figured that one out. We've got 3 more to do. We just have to be patient. Patience is like super important in mathematics. You need Zen-like patience often, very often. Yes, Zen-like patience, especially when you're trying to record a video like I'm doing, and people are doing construction road work right across the street and driving you up the wall while you're doing calculations and stuff. Well, you need Zen-like patience to endure all of this stuff. Okay, so, but mathematics can give you that, you know. You can think of mathematics as a form of meditation, and it gives you patience, certain serenity, peace of mind, and all of that. I hope you believe me. It's sort of true. All right, let's shift it by 3 pi over 4. So f 2x plus 3 pi over 4. I have avoided that mistake of shifting it wrong. Okay, what do I get? Let's recognize this curve. It's immediate. It begins at 0 and goes up, so I know it's sine 2x. Okay, we did it. Now let's go back. Let's go back and look at what we're doing. Yes, I have it right here. Sine 2x is done. 2 more to do. Very good. I'm close. I'm close to the finish line. Now we have shifted all the way by 4 pi over 4, which is pi. Okay, and you can see that cos has done 1 period here, cos 2x, in just pi, because it's 2 times faster because of the 2x. All right, so what do we have here? So I've done this shift, f of 2x plus 4 pi over 4, and this has resulted in, what is this? This starts at 1, goes down, that's cos. Cos of 2x. Okay, let's see, am I right? Is everything okay? Yes, we have done this one. Got 1 more left to do. The last one should be minus sine 2x. It should return full circle, right? Mathematics pun. Yeah, there are actually a lot of mathematics jokes, but no one laughs at them, not even mathematicians. So I don't know if it's worthwhile getting into them. Maybe I'll tell you some, but no one ever laughs at them. I remember telling a mathematician the famous Banach-Tarski joke, and he didn't laugh. So that kind of put the damper on mathematics jokes. Okay, so let's see. What am I doing next? I'll shift it all the way, shift the origin all the way by 5 pi over 4. Let's see what happens. F of 2x plus 5 pi over 4. I have done the shift correctly by adding just to x. What do I get? This is obviously minus sine 2x. It begins at 0 and goes down, so it's minus sine. Let's see if I'm okay here. Yeah. Okay, we have returned to the beginning, back to square one, derivative 1, same as first derivative. So I have everything done. Oh yes, let us not forget this factor here. in front of everything. We'll put everything together. We begin with cos, okay, and we are shifting cos, so we can now do like this. We write yn, which is the nth derivative, dn over dx cos dx and cos squared x, and this is 2 power n minus 1, okay, cos of 2, now do the shift properly, x plus n pi over 4. And this is my final answer. So I have now, in the form of a function, f of n x, just one function for all of these derivatives. And I can write it also in a little bit different way, like this cos. I can multiply this out and you get cos 2x plus n pi over 2. So that, I think, again, this is really beautiful result. It's just beautiful how this all works out. It's really worth, I think, really worth thinking about. It's really something. Well, okay, that's it for this video. I hope you liked it, and if you did like it, then click like, and of course subscribe, and leave a comment. Okay, and I hope to see you next time. But before we go, I want to have one more look at this beautiful answer. It's just so beautiful. I really like it. Just incredibly elegant answer for the nth derivative. But I want to point out that this really works for n is greater than or equal to 1. Don't try to do the 0th derivative with this. It won't work, but it's for n greater than or equal to 1. And I will see you next time.